There we go. All right, so this is where we left off the other day. We can still work through it. Try not to check your notes, but if we're treating these with a strong base, meaning, and if we call it a strong base, again, that's also a strong nucleophile, but by calling it a base, we're saying, basically hinting it's going through elimination, not substitution. Really, we would get some substitution product as well, but for the sake of this, that's what using the word base rather than nucleophile means. So we're treating this with a strong base. What are our possible products, and which one's going to be favored?
Since it's two, it's going to be concerted mechanism.
So concerted mechanism, yeah.
We're going to have a stereochemistry flip.
Not quite, because we're not going to wind up with any stereochemistry. We're not going to wind up with RNS, right? So substitution, concerted substitution, we get a stereo. So we'll be pulling this off. And so we do have to worry about the stereochemistry, but it's not that flip. Right, we make the alkene. So, and remember, that means we have to pull a hydrogen off of the adjacent carbon, and this carbon doesn't have a hydrogen on it, which means we can't do anything with this one. So that right there is going to limit our products, because we can't put 5 bonds to a carbon. So we could have that product, and it's actually harder than you think to, when you're just counting off the carbons to make them cis. So those are our two possibilities. They're both equally substituted. So which one would we expect to see more of?
The one on top.
And why? These things are big and in the way, right? That push on each other. That's just sterics, basically. And
It was because it was the E.
because it's the elimination, yeah, exactly. This is the E conformer, and we're going to see that more because that's the one that comes from. If we start from the Newman projection of our compounds. No, sorry, I looked at it the wrong way. We have a T-butyl group going straight up. And the hydrogen down into the left. So we're looking along this carbon bond. So this front carbon is one that I circled right there. So fluorine down to the right. Oh, good. T-butyl group straight up. And the hydrogen down into the left. The hydrogen's not shown on there. It's a skeletal structure. And then the back carbon has an ethyl group and 2 hydrogens. And the way it's drawn right now, the ethyl group is going straight down. And so with this in mind, we have to remember that our leaving group has to be periplanar and anti. I kind of skipped over that slide because it's a fairly self-explanatory. Basically, our base, we don't want them to be the hydrogen and that's leaving and our leaving group to be in the same plane facing the same direction, because then they would have to be eclipsed, which is less stable, plus then your base physically has to come into the same space as your leaving group. Your leaving groups are typically big, bulky groups. So I didn't define syn periplanar versus anti-periplanar. Anti just means opposite, syn means the same. So it's always going to be anti-periplanar, meaning we want this is the hydrogen that's going to be leaving, chlorine is leaving over here. And our two possibilities for the shape it could be in that has a hydrogen anti to the chlorine are the one I've drawn here, or if we rotate everything on the back carbon, that's also valid, but that puts our ethyl group right next to the T-butyl group in that Gauss position. So that conformer is less stable because that big group and that big group push on each other. Physically, they take up a lot of space. So that's why we see the E product predominantly. Because when we have two choices for which hydrogen we can take, we're going to take the one that gives us, this starts from the more stable conformer. All right, so for B, the same molecule except that we've added a methyl group onto the second carbon, which means we're taking away one of these two hydrogens. I used to finish this up. So there's our major product for part A. And with the T-butyl group being fairly large and ethyl's not that big, it'd probably be in something like a 70-30 ratio. So a significant amount of this, but definitely favoring this. But we're not talking a 99-to-1 situation. If we replace one of these hydrogens with a methyl group, so if we look along the same line here, the back carbon, so up and to the left, because it's behind the board. So if my view is parallel to the board, it's over here, it's on my left side, if it's sticking into the board. So that's this hydrogen got replaced with a methyl. Now all of a sudden we don't have two choices. We only are going to make one product because there's only one hydrogen that we can remove, and it has to be anti-periplanar. And so this all gets twisted over, we get our hydrogen in the right spot, which puts our methyl group down, our ethyl group next to the T-butyl group. And so then when we take away that hydrogen and the chlorine and everything flattens out into sp2 hybridization, we're going to put the ethyl is going to be right next to the T-butyl. So in this case, we wind up with this product. All right, so it only gets that tricky when there's only a single hydrogen that you can remove. As long as there's two hydrogens on your alpha carbons, this doesn't really become an issue. You just put this biggest, bulkiest groups on opposite sides for your major product. But when there's only one hydrogen on an alpha carbon, you can only have one product. And to know whether it's the E or the Z, you kind of have to go through this step. All right. So similar to SN2 reactions, elimination reactions have their own relative reactivities, the relative rates of reaction. So what that means is, so for SN1 and SN2, we could say, okay, well, SN2, we needed physical access to the carbon that had the leaving group on it, right? In order for our nucleophile to come in and attach. We still have the similar issue, hey Sarah, with this, except that our base doesn't need physical access to the carbon with the leaving group, it needs physical access to the alpha carbon, carbon 1 removed. Right, so that means primary versus secondary versus tertiary. That affects E1, E2 a little bit, not as much, because we don't need to get right in there as much. And frankly, because our hydrogens are not as protected as the carbons are, right? If you think about what these structures look like, let's look at, just clean this up. If we just think about, okay, this molecule trying to go through an SN2 reaction, if we have a nucleophile coming in here and trying to attach opposite from the chlorine and the chlorine leaving at the same time, this hydrogen is still on a tertiary, or that'd be a secondary carbon, but the hydrogen is physically not as close to the center of the molecule. Hydrogens, by definition, have to be the end of a chain, right? Because they can only make one bond. So the hydrogens are much less protected and less surrounded by electron clouds and other sterics. The hydrogens are just sort of sitting out there on their own, as it is anyway. So that means that E1 and E2 are not as affected by primary versus secondary versus tertiary. The only thing that really affects it is if it's a primary alkyl halide, when our leaving group leaves, remember that if it's E1, that means it's the stepwise reaction. And the first step is leaving group leaves. So we have the same problem with E1 and the primary alkyl halide that we had with SN1, right? You can't make a primary or a methyl carbocation because they're just not stable enough. So it's less about sterics. The sterics don't come into play as well. So all of them can go E2. But you can't have E1 if it's primary. All right, so what does this mean? This is a fairly complicated, this is actually two tables from the book that I grabbed and put next to each other. There's a lot of wrinkles on this and there's a lot of duplicates, right? You've got primary alkyl halides down here, but also up here. Right, which means it's a possibility, and since our nucleophiles are also usually bases, we actually we have all of this happening at the same time. E1, E2, SN1, SN2 are all possibilities with a given set of reactants. We just need to say any of them we can eliminate by saying, oh, well, it's a primary alkyl halide, therefore at least I can get rid of the first order reactions. Or it's in a polar protic solvent, which means I can get rid of my SN2 because it's not going to be a strong enough nucleophile. Or because it's stabilizing the intermediate for the first order reactions. Right, so we basically have to kind of go through a flow chart of decision making for given the set conditions to decide which of these mechanisms is going to be most likely at any given time. And they all have their own sets of wrinkles. For example, for E2, we have to worry about, where are the hydrogens on the alpha carbons, and how many are they, and what are we getting the E versus the Z? And we want to make most substituted alkenes. We don't have to worry about any of that for substitution. But substitution, we have to worry about things like the SN2 reactions that flip the stereochemistry. Right, so they all have their own set of complications. And just a reminder, we've talked about this second question before, down here. If it goes through a carbocation intermediate, which is both of the first order reactions, what does that do to stereochemistry?
Is there a mixture of different things?
You're going to get a mixture of different things because it's not concerted, and these carbocation intermediates are planar. So whatever, if it's a substitution, if it's first order substitution, whatever is attacking and reattaching in that empty p orbital could come from on top or from on bottom. So you get a mixture of R and S. Of course, cis and trans if you're talking about a ring structure or something. For the concerted reactions, they're more stereospecific because everything has to be in just the right way, just the right conformer for the reaction to happen. All right, so I grabbed this is from the end of chapter material. And the end of chapter material is very helpful in this textbook. I really like it because it breaks down a lot of what are the key skills from this chapter, what are the main takeaways from each of the sections. It's pretty helpful when you come back to studying. And it also has this section, so this is predicting the products of substitution and elimination reactions. The first thing you have to do is know which mechanism we're dealing with. Right? And so depending on what your base or nucleophile is, that's going to dictate, and what your alkyl halide looks like, is it primary versus secondary versus tertiary, that dictate which mechanism is favored. And solvent plays a role as well, but solvent is typically less important than these other variables. And so if we have, I guess I'll start over here. This is a pretty useful list because these are some of the most common nucleophiles and bases, and it sort of breaks them down as whether we treat them as a base or a nucleophile, which again, like I mentioned earlier, tells us whether we're looking at elimination versus substitution. If it's a strong base and it's also a strong nucleophile, then that means we're going to get a mixture of substitution and elimination products in most cases. If it's a weak base and a weak nucleophile, then that's going to be a little bit trickier, but we're still probably going to get a mixture of substitution and elimination, but the difference between these is generally that these ones are going to go through concerted mechanisms because they're so strong, and these are going to typically go through stepwise reactions, if at all possible. If it's a strong base but a weak nucleophile, this is going to be most of your sterically hindered bases as well, so TBUOK could be on here as well. Now, those are the ones that the base itself has lots of what my OChem instructor would call spinach around it. It's got lots of junk around it that's kind of taking up space. So it's a strong base because you still have an oxygen with a negative charge that wants to grab a hydrogen or act as a nucleophile. But in this case, the big bulky groups around it mean it can't physically get into that active carbon, so it'll settle for just being a base instead. So if it's a strong base, weak nucleophile, basically we're only going to see elimination. So those are actually some of the easiest ones to deal with. And not only do you only see elimination, you're going to get the Hoffman product. You're going to get the least substituted alkene, as opposed to the Zaitsev product. If the reverse is true, if it's a weak base but a strong nucleophile, So now we're talking about things like the halides. They're really weak bases. They're really not very good to put them in as, because these are all the conjugate bases of strong acids, right? Hydroiodic acid, hydrobromic acid, hydrochloric acid. Those are all strong acids, which means that these are not very good bases. They won't hold on to a proton. But they can still be a strong nucleophile because they still have a negative charge. They're still going to be attracted to partial positives. They're just not good at holding on to protons. Right, so in this case, they're not going to see any elimination. You're going to see all substitution. And for the most part, concerted, although that's now we're looking at splitting hairs and looking at is the primary versus secondary versus tertiary to determine whether it's going to go SN1 or SN2. But we know it's not doing any elimination. All right, so when we get I like this chart because the colors are easier to parse than text, and because it does everything that we just discussed, it kind of lays out results of that logic pretty clearly. Strong base but weak nucleophile, no substitution, and concerted. This is a stronger reason. It's a strong base because it's unstable on its own, so it's going to go in there and it's going to take a hydrogen. Strong bases that are also strong nucleophiles, it's still all going to be concerted, but whether it's elimination or substitution depends on whether your alkyl halide is primary, secondary, tertiary. Right, it's tertiary, it can't go SN2 because your nucleophile can't get in there and attach to the carbon. There's too much spinach around. I used to think that spinach was just my OChem professor being weird, because he had a lot of odd sayings. He used to keep track of weird things that he said and write them in the margins of our notebooks. But apparently it's actually a fairly well accepted term in organic chemistry, because I actually saw it in a textbook one time. So, and I don't think he had a hand in writing the textbook. Although you might be surprised sometimes who gets their opinions and their wording in textbooks occasionally. But so, if there's too much spinach around, no substitution, still concerted though. So you have the concerted elimination. If it's a weak base, strong nucleophile, it's all substitution. And whether it goes SN1 or SN2 depends on primary, secondary, tertiary. Basically, you only get SN1 when it's tertiary and there's no other options, basically. If you have a weak base that's also a weak nucleophile, then it's going to go through, basically the primary and the secondary alkyl halides just won't react appreciably. But you can get SN1 and E1 happening if it's tertiary, because that carbocation intermediate is stable enough that you can wind up with that happening. And this one's a little wishy-washy too, though, because this is one where you can actually get it to react if you do it in a polar protic solvent. If it's in a polar protic solvent, that stabilizes the intermediate enough that you can actually get a secondary carbocation at a measurable amount. So that one may be more of a question mark. It's still going to be first order. But with a polar protic solvent, you can still get it to react, and you would still get some product that way. It would be a mixture of E1 and SN1. All right, so we have four mechanisms that go in two major directions, and there's two ways of breaking them up. First order and substitution elimination, right? So you can have sort of a Punnett square of mechanisms when you look at our possibilities. The first order, second order, substitution, elimination. Right, so they have their similarities in both of these dimensions. And so we just need one way to sort of zero in on which of these is going to be favored. But one of my favorite ways to ask a question that relies a little bit less on you being able to interpret the finer details is I'll either tell you what mechanism to use, or a lot of times I'll say, ignoring things like picking a mechanism, draw the products of all four mechanisms for a given molecule. Because I like that one a lot because it basically, you can get, if I pick my correctly that has the alkyl halide, you can get a lot of differences, whether it's first order versus second order, because you'll wind up with rearrangements if it's first order, but not if it's second. And obviously substitution and elimination are going to give you different products as well. And so when I say draw all possible products from all mechanisms, I mean go through, look at SN1, draw all the products that SN1 makes. Look at all the products SN2 makes, cross out any of their duplicates. Look at all the elimination products, first order and second order. So that can be a long problem. That's typically at least 10 points, if not 20 points on the final, will be one of those. Ignoring all the stuff like solvent and strong base versus weak base, just show me everything that could happen. And then the section after that is, now how do we pare this down and decide which mechanism is favored. And usually I make it two. We pull up the last year's test. But basically what I'll do is another 10 points will be, here's a set of reactions and conditions. Tell me which mechanism is favored. So that's multiple choice basically. And then the page after that is the exact same reactions. Draw me the major products for each of them. And that way, if you get the mechanism wrong, but you draw the right products for that mechanism, I don't have to mark you down twice for the same mistake. Right, so it seems redundant, but it's because I'm trying to help yourselves. And I'm not sure. Last year's final, I think I made significantly different because it was open book, and yours won't be. And I'm having trouble. Dropbox is not running. All right, hang on. Well, we'll come back to that after the break, probably. All right, let me go back. We'll just go back here for now. We'll talk about structure of the final more next week anyway. And the last piece here, just to consider geochemical and stereochemical requirements. So that's when, once you've picked your mechanism, now you have to say, okay, SN2 means no rearrangement, but I do have to worry about my stereochemistry flipping. Or E1 means it goes through carbocation rearrangement, or it could go through a rearrangement when it's a carbocation intermediate, which could affect my products, right? So this is the step after you pick your mechanism. That's when you come in and start looking at, okay, specifically what's going to happen in the course of this reaction now that I've picked which pathway it's going to go through. And a good way to study this is there's a link to a cheat sheet that was developed by West Virginia University that I wouldn't say it contradicts with our textbook, but there are a few points that this takes into account that our textbook in its summary section kind of glosses over. The textbook is really good in the text, but in the summary, it kind of leaves out some of those details like solvents. And we'll talk about heat as well in a second. But basically, this is just another way of looking at these two dimensions, first order versus second order. Sorry, I'm not showing you. It's also not colored, which means it's not as fun to look at, but and this also brings in benzylic and allylic. Generally speaking, when these are the cases where we would have resonance, right? And these cases react very similarly to secondary carbocations, because you're not usually going to have a tertiary carbocation or a tertiary carbon with a leaving group that necessarily has a lot of resonance nearby, because there's typically there's lots of sp3 carbons around, not sp2 carbons. It's not impossible, but these tend to fit into the category more neatly with secondary halides. But basically it has it just arranged a little bit differently. It has the mechanisms as the columns rather than strong base, weak base. Right, so just another way of organizing things, and this has lots of details built into it, so this is a good one to study from. And it also has a better definitions of strong nucleophiles, weak bases, weak nucleophiles, weak bases, strong bases, weak nucleophiles, strong nucleophiles, strong bases. And again, some of this changes a little bit based on solvent, and this one doesn't take solvent into account either, but it does bring in temperature. And we'll talk about how temperature factors in a second. All right, so that link is in the slides. It's also posted, I think, in the resources section of the website. But if you can't find it, just let me know. All right, so let's do some of these big, broad, all possibilities questions. Draw all elimination and substitution products, including stereochemistry. So even though we know this is a big bulky base and it would only really go through elimination reactions, I want you to practice by drawing substitution reactions for it anyway. Because those are going to be the trace products that are present in very, very small amounts. And I will walk you through the process for this first one and then turn you loose on the second one to practice, to work your way through it on your own before we go over it. I typically approach these just in the same order that we learned the mechanisms. SN2 was the simplest, right? Usually only one, it is always one step. It's a concerted reaction, which means only one product. So SN, if we were drawing the mechanisms, you don't have to for this. It would look like that. So basically we're going to get that stereochemistry inversion. The ethyl and the methyl are even drama staying mostly where they were. The hydrogen comes out towards us now. And in the back now we have this big T-butoxide attached. Right, and it's all three of these go through the umbrella flip. But when it comes to drawing it, a lot of times what's easiest is to treat it like these ones, like they're standing still, and this one is flipping more like a light switch. Pick one of them to flip, to push, and leave the others drawn where they are, just for the sake of not confusing yourself when you're drawing these, but realistically, they are all three moving. This is just the fastest way to draw it. So that'd be our SN2 product. What would our SN1 product? So still substitution, but going through a carbocation intermediate. Well, let's just start by drawing the intermediate. So these all start with leaving group leaves. And so our intermediate would just look so I turned it into skeletal structure, but same thing, an ethyl group, or carbon that had the leaving group, and a methyl group. Any rearrangement to worry about? There's no way you can move the charge to make it more stable, right? To move a hydrogen to make it a tertiary. So no rearrangement. So that means that one of our SN1 products is the same as the SN2. But we're also going to get the opposite isomer as well, because our nucleophile could attach in either direction. So we also wind up with the version that has the oxygen pointing up towards us. And as long as we have a carbocation intermediate drawn, might as well consider E1, right? So E1 is going to go through the same intermediate because it's first order, meaning stepwise. And again, no rearrangement happening, so we just have to look at, if it's E1, we're looking at what alkenes could we make from this intermediate. Which adjacent carbons, which alpha carbons, have hydrogens that could be removed. So there's 2 hydrogens here, 3 hydrogens here, so we could get products going both directions, with the alkene going both directions. And last but not least, we need to watch our stereochemistry. This has a stereoisomer, right? And because this carbon, the alpha carbon that gives us that product, has 2 hydrogens, we're going to get both possibilities. So we will also get Z2-butene. So I also like these problems because they're a decent review of all mechanisms that we've done. So now we have those in our head. This is what we go through for each of these mechanisms. So which of these is going to be the favored product out of everything we have written on the board? So we had to decide whether it's substitution or elimination too, right? Not just E1 versus E2, but which of these 2 boards we're looking at. So secondary leaving group. So that means that's middle of the road. That could go either direction. But that's a big bulky base. Right? It's a good base, but it's a bad nucleophile because it's got these carbons around it. So we would not expect to see any substitution. And we also, our E2, I guess we did not call out E2 versus E1. Your elimination reactions, you're going to get the same products for the most part, whether it's first order or second order, unless there's a rearrangement happening. So regardless of if it's first order elimination or second order elimination, we know it's going to go elimination. And out of these two, we can pick which one's going to be favored because this one has the sterics, or has minimized the steric repulsion. So out of these two, it would be the trans, the E configuration. But because it's a big bulky base, it makes the Hoffman product, not the more substituted product. Right, so this would be our major product, just based on what our base / nucleophile is and what our leafing group is. All right, now that I worked through the easy one, you guys can work on the tricky one. So I started with the concerted, with both of the concerted in this case. Any guesses why I would do that? One-step reactions are simpler usually, right? SN2, if we're starting from a specific stereochemistry, SN2 will only ever give you one product. And E2 will give you more products, but at least we don't have to worry about rearrangement, right? And this carbocation intermediate is interesting that way, because we can have rearrangement. And I don't think when I wrote this problem I intended to do this, but it actually could rearrange in two different ways, right? Because if we had a hydrogen move over from our isopropyl group, we could get a tertiary carbocation, which is more stable than secondary. But a hydrogen over here could migrate too, and then we have it's still a secondary carbocation, but with resonance. And resonance goes a long way, especially when it's a whole benzene ring. We get a bunch of different resonance structures then that are all, and the more resonance structures we have, the more stable things get. So I've actually just been sitting up here this whole time you guys have been working, trying to decide in my mind which way it would be more likely to react. I think it would move towards resonance. Resonance, I think, is a bigger stabilizing factor than being tertiary versus secondary. So we would have rearrangement happening to put our carbocation right here. So we get this intermediate instead. And now this one can go through substitution and elimination as well. So if it was substitution, we would get the R and the S that puts the oxygen on this carbon. And if it goes through elimination, well, the nice thing about a benzylic carbocation when it comes to elimination is there's only one direction we could draw the pi bond, right? So for SN1, we would get R and S. And for E1, we get a mixture of the Z conformer and the E conformer. I keep saying conformer, stereoisomer.
If you did the SN1, would you get any of the products where the positive charge is rotating around the benzene ring?
No. Mostly because if we actually did the substitution on the benzene ring, you break up the benzene ring. So those resonance structures are there, and they put a partial positive on alternating carbons around the benzene ring. But if you actually added something there, you break up all that resonance now, and it doesn't stay as a benzene ring now. So because you would be totally breaking the aromatic ring to do that, we won't see that.
Overall lower stability.
Right. Remember when we talked about electrophilic substitution on benzene rings last year? The first step was what we just described, where you basically do an addition reaction to a benzene ring, made one of the benzene ring carbons sp3 temporarily, But then the next step was always something got booted off so that it could reform the benzene ring.
So many wrinkles.
Turns out the real world is complicated. And we haven't even gotten into things like cells and proteins and enzymes and feedback loops and things like that. All right, so hydroxide is strong base and also strong nucleophile, right? That's one of our classic examples of strong base, strong nucleophile. So which mechanism is going to be favored? Secondary leaving group. So that doesn't really narrow it down that much, other than first order reactions generally only happen when it's tertiary, or when there's already resonance happening. So you won't get your leaving group leaving just to make this, which could then rearrange. That's too many steps, which is good because that simplifies things, right? So we're only looking for, if it's secondary, it's going to go concerted. It's just a matter of, is it concerted elimination or concerted substitution? And that one, we can actually, so we're right here, right? Secondary leaving group, strong base, strong nucleophile, mixture of E2 and SM2. More E2 usually. Especially considering that we have several very large groups. Even though it's secondary, there's still that phenyl ring, the benzene ring, and an isopropyl group around our leaving group, our active part. Means that that probably favors elimination even a little bit more than normal. So, with that in mind, we're going to favor these three products. And basically all of the stepwise reactions, we basically just say, okay, well that's going to happen in insignificant amounts. Unless we tweak it with solvent or doing something like that. So, out of these three elimination products, which one's going to be favored? It might help if I redraw them a little bit so they're not right on the seam there. Did I lose the carbon somewhere? No, that's right. The problem before when we were dealing with the, or after it did the rearrangement when it was an isobutyl group instead of an isopropyl, it's got me overthinking it here. So which of these three options is going to be most favored? We go Zaitsev's rule or Hoffman product? Zaitsev's rule says the most stable alkene is the most substituted, which would have us predict this one. However, there's always a however, resonance makes things more complicated. If we make these products, we have a pi bond that's conjugated with the benzene ring that can resonate and draw resonance structures with the benzene ring. So again, I probably was just trying to mix it up when I made this. I don't think I was trying to write a trick question. We would expect it to go Zaitsev's rule, but maybe not nearly as favored as normal. Zaitsev's rule with hydroxide is usually something like 70-30, favoring the more substituted product. In this case, it might be closer to 50-50, or maybe even slightly favoring these because of the extra resonance. And this is a good example of if I happen to do this on a test and accidentally make a problem more difficult than I need to, or you just are having a hard time deciding because you recognize there's two possibilities and there's arguments in favor of both possibilities, pick one and write out your logic. If you do this one and say, because Zaitsev's rule, or if you pick this one and say, because you get extra resonance, especially if you write something like, well, I know it goes counter to Zaitsev's rule, but you get extra resonance. Even if you didn't pick the one that I was anticipating everybody picking, that's still, if not a full credit answer, depending on the exact circumstances, it would still be very close to a full credit answer. So when in doubt, just explain your logic.
And it would be the less sterically hindered.
The less sterically hindered one would be the major product in all likelihood. And then actually statistics comes into play here, since if making it conjugated with the pi bond is 60% of your product is one of these, but then that 60% is split up, 60-40. Yeah, 60-40. 60% of 60% is what, 36%? And 24%, which means this one's 40%. So it is still the major product because the one that had more resonance actually had two stereoisomers that were competing with each other as far as the percentage goes. Right? So sometimes the statistics and the math actually make it even trickier because we didn't have enough to think about yet. So again, explain your logic, even if you don't go into it that depth. I think it's going to be one of these two, the less sterically hindered of these because of the resonance would still be a totally valid answer, even if we work through the numbers, it would actually wind up being this one's more likely, just purely based on the fact that it only makes one stereoisomer. Well, synthesis is tricky. You actually want to make one of these three, and it's going through this pathway. It's really hard to actually try to maximize the one that you want, because no matter what you do, you're losing like 70% of your yield because it's not the version that you want. All right, it's about time for a break. These pages are effectively just walking through the logic. It's a flowchart version of what we've been talking about. You can decide first order, second order. Is it concerted or stepwise? That eliminates a lot of choices, right? And then from there, you can split it up and say, okay, is it substitution or elimination? Or you can do it in the other order as well. You could try and decide substitution versus elimination first. But I think there's more similarities between the first order reactions and second order reactions than there are between elimination and substitution. All right, so key things we're looking at is it primary, secondary, tertiary? Strong base, strong nucleophile. How strong is your base? How strong is your nucleophile? Which of those categories fit in? Then there are two other things. I guess we'll take our break and we'll come back and we'll finish this up and really get into the splitting hairs portion of picking our mechanisms. And when you can't make a decision easily based on category of your bases, things like that. Let's go back to 10 after, and then we'll get into NMR after that.
Yeah, next quarter can be awesome.
Lots to pay attention to, huh?
For me. Yeah.
So you'll be in,
Will this be this class and linear algebra? And
but you'll be done with physics.
yeah.
Okay.
Done with physics, and I have English classes in this quarter too, which I won't be doing next quarter.
That's good because those are, I'm trying to think, but I believe that my second year of college that I know I had OChem 2 and linear at the same time. I'm trying to think of what I had with that. I also had analytical chemistry and I think a lit class at the same time, and that was a lot. But I wasn't working nearly as many hours as you've been doing. So, and lit class was fun, but it was not nearly as stressful. And it was a break when I was studying for lit. It was on a break from studying my other classes because it was more fun.
Yeah, I'm also fitting in science club, art club, jam sessions every week, and then also trying to sleep in.
Yeah, that's the trick.
Yeah.
I didn't, like I said, I played rugby and I tried to surf as much as I could, but I wasn't playing music, and so surfing was on my schedule, which was nice. You can do that whenever. When you have to work other people's schedules around all of your other stuff, that's when things really start being stressful.
The jam session thing is definitely like every week I'm just like, maybe I shouldn't do it this week, and then we have to start playing, and it's exactly what I needed.
Yeah. No, you gotta keep those kind of hobbies. It's just they're stressful when you're not doing them because it's one more thing on your calendar. But when you're actually doing it and afterwards, it's much better. It's just, and if you have a recurring weekly thing, that's the best when you don't have to find time when people's schedules aren't changing week to week.
Yeah, I mean, a lot of times it's just me and Grace, I'll play drums and she'll play sax, and we're just kind of go frantic. And that's pretty nice. But
yeah.
Sometimes, we'll get people together, and a couple of the people who've been playing with their drummers primarily, so they don't play keys or bass.
Hey, Carl's bass player. His wife plays keys.
Oh.
And Carl plays a little guitar too, I think predominantly. When they're playing in groups, I think he predominantly plays bass.
Okay. Yeah, I remember I talked to him about that. He writes music and he plays guitar and keys and bass.
Yeah, maybe he plays bass just because it's harder to find bass players than guitar players usually.
Don't mean to be rude, but I got to point out that tag again, right?
Yeah, I keep feeling it. I just noticed it while I was teaching. It's on plastic though, so I can do that. I was hoping it wasn't one of the ones that's like safety pinned in there. Go to my office, take off my shirt. Thank you.
Yeah. Those are the kind of details I never noticed.
Oh, yeah?
Yeah, I don't remember what color people's cars are. Or like, really notice, oh, you were wearing the same shoes as you were yesterday.
Oh, yeah.
I never said I was good shoes.
I usually notice new shoes, if they're shiny and they're new, I was like, yeah, those are fresh, clean. I usually notice it's something like that or something good. More like fresh, clean ones.
If I'm lucky, or if it's like something drastic, I might notice if somebody like dyes their hair.
Haircut?
and it fly right by me, unless it's like a robot. Yeah.
So you just dreaded up all their hair or something, like, whoa, that's noticeable.
I can actually just, it takes a while after getting a new car for me to remember like all the areas. It's so crazy like how little I get into cars.
Interesting.
Well, that's the color my old car was. And that's another thing. Then also complicating things in a fun way is that my neighbor and friend who lives across the street has an identical red Subaru. And I've run into her at the store multiple times. We will be there at the same time by accident by going to her car.
I've done that before, especially around town. If you have an early 2000s Subaru, I've actually tried to open the wrong car door before.
I have a couple of times at City Drive. It's really weird when people come out here and trying to
Yeah, and then you hope your car is nearby enough so that it's like obviously, oh, that's what happened. Not I was trying to break into your car. Okay. Let's talk about other ways we can decide which mechanism is gonna be favored. A lot of times the easiest decision is first order or second order, because you are really not going to go first order very often unless it's a tertiary alkyl halide. Right? It's got to be a really stable carbocation intermediate. But there are some other mitigating factors. If it's a protic solvent, then that stabilizes that intermediate a lot. Especially if you also have a weak nucleophile or a weak base. So if it's a protic solvent and you have a weak base, weak nucleophile, that's that question mark box that was over on the right of the colored chart, where it's like, okay, well, it's not going to go concerted, but you can get some of the first order reaction happening. It'll be a lot slower typically, but you can see that happening. So weak bases, weak nucleophiles, low concentrations favor first order reactions. Why might that be the case?
Statistically less likely to run into each other?
Yeah. If you look at the rate laws, so we say, okay, let's leave elimination off of it right now. If we had the rate of SN2, the rate law looks like this, right? If you have the rate SN1 is just K times the concentration of our bromide. And so if these are competing with each other, if these are both happening at the same time, well, you can really slow this one down if you have a really low concentration of your nucleophile. And so high concentrations are going to favor the second order reactions because statistically it's easier for things to run into each other. If you take that concentration and you lower it, we can skew it towards the first order reaction a little bit. That's a mitigating factor. That's not the dominant decision when we're deciding first order, second order. It's mostly how strong is your base or nucleophile, and is your alkyl halide primary, secondary, tertiary. Those are always the two most important things for this decision. If you're in an aprotic solvent or nonpolar, it basically won't go first order. First order reactions in general happen way slower because you have to make that unstable intermediate. And so if you're not stabilizing that intermediate with a protic solvent, basically the first order reactions won't happen. So when it comes to deciding between substitution and elimination, that's when it comes into, okay, is it a better nucleophile or base? If it's a good nucleophile, but a weak base, you're going to go substitution. If it's a good base, but a weak nucleophile, like our sterically hindered ones, it's going to go elimination. And if it's a weak nucleophile and a weak base, you get both of these. If it's a strong nucleophile and a strong base, you'll get both of these in some ratio. Right, and so if there's steric hindrance, the more spinach you have around your active carbon, the more likely it is to go E2 as well. Or sorry, E2 or E1. More likely to have elimination if there's lots of junk around your active carbon. And the one last thing I want to look at is temperature actually can skew this as well. When you're deciding between substitution and elimination, temperature plays a role. Temperature favors, high temperature favors elimination. And it's because of our Gibbs free energy equation. Because if you have an elimination reaction, we write out the whole thing and balance both sides of it. Just pick a simple molecule. If it goes through elimination, we would get these products. If it goes through substitution, we get these products. Why does the temperature favor this pathway? Why does high temperature favor elimination? What's different about these? That is, we can approach in a general enough level to just look at it here. Delta H is not all that different necessarily. We're making a bond that's slightly less favorable here. Rigging?
So that entropy is more molecules being made.
Yeah, we started with two separate molecules here, and we ended with 3 molecules. Versus starting with 2 molecules and ending with 2 molecules. There's really no net change in the entropy here. You have the same number of distinct pieces. But we went from 2 pieces to 3 pieces here, which means entropy, the increase in entropy for this reaction means that the temperature plays a role in determining which one's favored. Right? High temperature reactions are going to favor elimination. Low temperature is going to favor substitution. Well, at the very least, it just makes this second term smaller. And the enthalpy is the energy in the bonds, right? And sigma bonds are more stable than pi bonds generally, unless there's benzene involved. All right, we're going to skip this one for now. And we've got half an hour to talk about Nmr spectroscopy. And this is when I'm also going to post my lab lectures from last year that I still have recorded for IR and NMR, so that I think they're probably better quality recordings, because I was working from my desktop and was recording the slides on Zoom, so I think that they might be easier to understand as a recording. So I'll post those links as well. NMR spectroscopy is not, it's very vastly different than IR spectroscopy, but it's still spectrum measuring how much light is coming from a sample or being absorbed by a sample. The difference is in how much energy is in that light. IR is relatively high energy light compared to what we're going to be dealing with here. NMR spectroscopy looks at basically the magnetic field. Every nucleus that has a non-integer number of nucleons, remember nucleon is a neutron or a proton. If you have a odd number of nucleons, then you actually have spin inside the nucleus. The nucleus itself has spin, just like an electron does. So if you have non-integer spin, what that means is an odd number of protons plus neutrons, an odd mass number, then that nucleus has a magnetic field. And just like a magnet, we can apply a magnetic field and basically get all of the nuclei to line up the same way, just like iron filings line up when you put a magnet next to them. It turns out it's not a very much, not a very large magnetic field, so we need a really, really powerful magnets to do this. But that's what, and this is, NMR is the proper name for what you know as MRI. MRI are actually, it's using giant magnets to make the nucleons in your body line up a certain way and then measuring how well they flip back and forth. It just takes that information and processes it a whole bunch because there's kind of a lot of atoms in your body. And then that's what an MRI is. But in the 60s, when they first developed this, nuclear was a four-letter word. So they didn't want to call it nuclear magnetic resonance. So they called it magnetic resonance imaging. Right, so, and the general principle is that if we have, with our iron filings, if you think about putting one magnet next to a smaller magnet, there are two ways that it can line up with, the magnetic fields can line up. They can be in the low energy state, which is the state it wants to be in, where your positives and your negatives line up along with the magnetic field, or you can flip it 180 and have the fields competing with each other. But if you let go of it, what does it do? Flips back the other way, right? When it flips back the other way, that's going from a high energy state to a low energy state. And when things jump from a high energy state to a low energy state, what do? They what?
They release something?
They release something. Light, right? That's how LEDs work. We're just talking about larger gap in that case so that it actually gives off a photon in the visible range. Well, these energy states might not be very large because the magnetic fields of these nuclei are really small, but it turns out it's enough that we can measure it if we're really, really careful. And if the magnetic field is strong enough. So we have, I don't know if any of you have ever seen those photos of somebody actually accidentally put a desk chair with a metal base in the same room as an MRI machine. Maybe you've seen some of those pictures before, and they turn on the MRI machine and it sucks the chair into the machine. Yeah, that's a $1 million mistake right there. So we're talking about really strong magnets. But if we're careful and we get it down cold enough, because we want to minimize how much this is happening just randomly due to thermal fluctuations, then we can measure this. And so that's what NMR is. At its core is, with no magnetic field, no external magnetic field, all of the magnetic fields of all the individual nuclei are basically pointing in random directions. You apply a strong enough magnetic field, they're going to align either with it or against it. And the ones that line up against it will eventually flip back the other way and give off light when they do that. Right, so here's just another schematic drawing of that. With no magnetic field, everything's pointed randomly. You turn your magnetic field on, everything aligns with it, lowest energy state. If you then bounce radio waves off of them, you can get them to flip. So you can get them to go from the low energy state to the high energy state. And then, but then eventually they're going to flip back the other way. That's just like when I took my finger off the magnet, flipped 180 back to following the magnetic field. And when it does that, it gives off light. And that's the light we're measuring. We're talking radio waves though, so way lower in energy than IR light. So we have to have really sensitive equipment for this because there's a lot of background radiation, background radio waves happening that basically interfere and can override your signals if you're not careful. And so this is what an NMR spectrum looks like. And just like with IR, for some reason, it counts backwards. The low number is on the right-hand side. I don't know why. Again, it's just convention probably at this point. But it's a lot cleaner than an IR. Because IR had that fingerprint region, right? And they got a lot of peaks on top of each other and things like that. NMR spectra tend to be a lot cleaner. I guess I should also specify this is Proton Nmr. So remember that in order for this to work, we have to have an odd number of nucleons. So we can't actually do this with carbon very easily, because most carbon atoms have 6 protons and 6 neutrons. So the fact that it's the same number, or that it's an even number, but not that it's the same, doesn't matter at all that it's the same. You just have to, the sum has to be even. And then if the sum is even, then there's no magnetic field on that nucleus. If the sum is odd, we can do NMR with it. So there is carbon-13 NMR that we'll talk about next quarter probably. And you can do NMR with things like fluorine, because fluorine has 19, has a mass number of 19 usually. Those are probably the most common. Maybe, yeah, those are the most common for sure. Oxygen 13. That would be oxygen 17, I think, right? And oxygen 17, basically, you only get that. Yeah, it's normally 16. You can do it, but you have to create you basically need to make an enriched sample by using oxygen in your reactions that has 17 nucleons instead of 16 like normal. And then you can trace where that particular isotope of oxygen is. That's one way that they figure out different pathways in the cell. They do things like make glucose where all of the oxygens are oxygen 17. And then they see where those oxygen 17s wind up inside the cell. If they go to this organelle or that organelle, they get incorporated into the cell membrane, things like that. All right, so if we're just starting with proton NMR, the advantage to this is that almost all of our hydrogens have just one proton, right? Hence the name. If there was any deuterium present, it wouldn't show up. But it's less than 1% of the of hydrogen atoms are deuterium, so we basically just ignore it. Statistically, it doesn't make a difference. The number of signals that we see is going to be the number of unique protons. And by unique protons, I mean that we could tell the difference between them, that they're attached to different places on the molecule. Right, so protons that are attached to the same carbon or asymmetric carbon are identical. We can't tell the difference between them. They would all show up as the same signal on here. We'd only have one peak for all 6 of these hydrogens because they're identical to each other. if we, let's say we're looking at isopropyl alcohol here. That hydrogen is going to be different though. And that hydrogen is going to be different. So for isopropyl alcohol, we would expect to see 3 peaks in the proton NMR. Where they show up is based on electron density. Because remember, we're measuring the magnetic field of the nuclei, right? The more covered up our nucleus is by electron density, the more electrons you have around it, the more shielded it is. If it's shielded, it's going to show up further to the right. Further this direction you go is more de-shielded. So more electron density means further this way. Less electron density means further that way. So out of these 3 choices, which one would we expect to have the most electron density? Purple, green, or red?
Green.
That's a good, so what's your logic there?
It has like the most stuff surrounding it.
It has the most stuff surrounding it. Why wouldn't you pick red?
It's on the very outside of the molecule.
To the outside of the molecule, and what's it attached to?
Oxygen.
Oxygen, right? What does oxygen do to electrons?
Take things.
Right? It's more electronegative. So the green one, yeah, has more things around it, but it's actually going to be more de-shielded. The green and the purple are going to be close to the same amount of shielding. These will be a little bit more de-shielded because the oxygen is nearby. It's not directly attached to the oxygen, but it's attached to a carbon, which is attached to the oxygen. So the oxygen is stealing electron density from the carbon. The carbon, in turn, is stealing more electron density from the hydrogen. So the most shielded, actually, would be the purple ones. And then green would be really close to that, and the most de-shielded would be the one attached to the oxygen. Here's the other way that we can figure out which signal goes with which protons, is that the area under each signal is proportional to the number of protons. So not the height of the peak, but the integral of the peak. So just like with GC, right? You guys had to integrate the peaks to figure out what your mole fraction was. The area under the peak was proportional to the moles. In this case, the area under the peak of the signal is proportional to the number of protons that make up that signal. So we would expect the integral for the purple protons to be 6 times larger than the integral for the green or the integral for the red. These ones should be close to the same integral within sig figs. And the last one is actually the trickiest one to wrap your head around, because you have to think 2 layers deep, basically. The splitting of each signal is based on the number of nearby protons. So not the number of protons in the signal, that's the integral. The number of protons attached to adjacent carbons gives you your splitting. And I'll go into that in more detail in a second. So this is more information just about shielding. More de-shielded is further to the left. They also call that downfield. It's downfield when it's de-shielded. And it's upfield when there's more shielding. There's probably a football analogy in there somewhere. If you're more downfield, then you're more open. There's fewer people around you. And the other nice thing about this is that just like with IR, we don't have to be able to work backwards from, well, what's attached to what every single time. That's one way we can split hairs if we got a bunch of things close together. but certain functional groups tend to show up in the same region every time. So similar to IR, right? IR, if it was, you know, a big broad peak above 3,000, you knew it was not a OH group. If it showed up below 3,000, but close to it, then it was sp3 carbon hydrogen bonds. So just like with IR, we also have a list of characteristic frequencies. And it's not all that important to memorize these. This has a lot of detail to it. So here's our carbon that's adjacent to an alcohol. So that's what we were talking about just a second ago, right? The green one, we would expect it to fit in this range, in the 3.5 to 4 range. But a methyl group that is further away, okay, is going to be down in this region, right? So in more than one region. Right, so these are really tricky to wrap your head around when you're first getting started. But when you get used to it, there's a ton of information in here in the NMR. It just takes a little getting used to knowing what am I looking at. And so that's why I have it broken down. These are the 4 aspects to consider. The first one's the easiest. Number of signals is how many distinct protons we have. Second one is a lot like IR. It's still tricky, but it's a lot like IR. So at least we have some experience with that. Look where it shows up, consult your chart and see what is likely to show up in that region. And some of these are kind of broad. Like alcohols can show up, alcohol hydroxyls, meaning the hydrogen attached to the oxygen directly, can kind of show up anywhere in here. Depending on a lot of different conditions, what the exact molecule is and what, you know, what's the concentration even can affect where it shows up, because they're going to interact with each other a little bit. But some of them show up in really characteristic regions. For instance, X. There we go. Always show up in the same general region, and there's not that much that shows up there. It's not on top of a bunch of things, right? And so with that in mind, basically if you see a bunch of peaks in between 6 and 8, it's almost always going to be a benzene ring. And remember, it's the hydrogens on the benzene ring. And since sometimes there can be a lot of distinct hydrogens in that same region, you can wind up with spectra where you basically just have a big mess in that between 6 and 7 range. You can't really tell how many signals are in there and if there's any sort of peak splitting or anything like that happening, but we know that there's a benzene ring involved. And if we integrate and find the total area under the curve here and compare it to these others, we can tell, okay, are there 4 hydrogens on a benzene ring, meaning that there are 2 other things attached? Or are there 5 hydrogens on the benzene ring, meaning only one thing is attached to the benzene ring? Right, so the integration is going to play a role, and basically this should be a red flag, not a red flag, not like it's a bad thing, but like it should stick out. When you got a bunch of things on top of each other between 6 and 7, it's almost always a benzene ring. And then some of the others that are really characteristic that are really obvious is carboxylic acids. The hydrogen is really de-shielded, and same with aldehydes. They show up way downfield compared to everything else. Almost all of our sp3 carbon hydrogens are pretty shielded, and they're going to show up pretty far upfield. And sometimes we have to zoom in on it to sort of tell this is a peak, that's a peak, that's a peak. And this is tetramethylsilane. It's called TMS. And TMS is basically just used, it shows up, it's what we use to define 0, essentially, because the hydrogens on tetramethylsilane are all identical because tetramethylsilane looks like this. So carbon is more electronegative than silicon. So carbon actually pulls electron density from the silicon, and all of these hydrogens are identical to each other. So you get one peak that's very shielded. And so we use that to define, it's more shielded than pretty much anything else we would see in an organic molecule. So we just use that, it's just a big spike that shows up right at 0. We use that to define 0. And a lot of times when we look at these spectra, we don't even bother showing it. It's there and we use it to define 0, but that's where these numbers are coming from, because this shift, it's in units of parts per million, which is really technically a concentration unit, but it's not really in a unit we can do any math with or anything like that. So it's sort of arbitrary. So don't get too hung up on the exact numbers. It's basically like, like taking, writing down directions. Take your third right on this. You don't need to know the exact distances to figure out how to do something. You just need a point of reference. All right. So we go back to my list of most important pieces. Number of signals is number of unique protons. Location of each signal is based on shielding in what functional group it is. The integral of each signal is proportional to the number of protons, which means you have to be dealing in whole numbers, or at least really within sig figs. And so generally what you will do is when you take a spectrum, you go through it and you integrate it and you say, okay, well, you basically click this side to that side, and it'll basically integrate that area, just like you did by hand, well, not by hand, but in Excel for the GC. You would use the computer program to do that. They're designed to do that. It's basically doing the exact same thing. It's just more automated. So then you would look at it and say, okay, well, and when you first do it, you would just say, okay, pick your smallest peak, and you say, okay, I'm going to call that 1. And then when you measure your other peaks, everything should be a whole number, ideally. But if you have a compound where your smallest peak is actually 2 protons, if we called this 1, these would show up as 1.5 and 1.5. So we just have to be able to look at that and go, well, I can't have half of a proton. So really, this must be 2 and 3 and 3. And so when you do this, if you don't get a whole number, it should be something that you recognize as an obvious fraction. Right? So, if you came up with, if this was 1 and then you got 2.5 and 2.5, then really it would be 2 and 5 and 5. Right? So you would just wind up basically multiplying by integers till everything came out to be a whole number. This is the other common way that you see the integrals represented, is if you don't pick the peaks yourself, then it basically just gives you a red line on top of your spectrum. And that is the integral right there. But so basically all you do to integrate this is you measure the bottom and the top, and you physically get out a ruler and you measure that distance. And then here and here, and here and here. And the distances should be in whole number ratios to each other. You don't always need to get out, because they should all be whole number ratios or close to it, you don't always need to get out an actual ruler. We can look at this and say that's the smallest one for sure, right? You can't have less than 1 proton. So if we call this distance 1, we can look at some of these others and say, okay, well, there's my 1. That definitely looks like it's closer to 2 than 1, right? So 1, 2, and then if this is 2, That's definitely more than 2, right? But it's definitely not twice 2. Again, you can do this more rigorously if you actually just get it out and measure in centimeters, and the ratios make it pretty obvious. So, let's see. Bottom of my thumb, that's pretty much identical, right? And then we've got over here, which is almost a whole marker. So this was 3. It's probably 3. Definitely doesn't look like it's 4. I say that and then I try to write 4. And so all of a sudden, that actually gives us a ton of information, because not only do we know where the shielding, roughly what's going on, in fact, you might not be able to see it, but this is 6, that's 6 right there, so this is 6.5. Big, complicated mess of signals between 6 and 8, that's a benzene ring. It's a benzene ring specifically that has 3 hydrogens on it. And then we have 4 other signals. Well, that tells us that we must have, without even knowing the formula for this molecule, I could actually take a guess at what the structure is. Because a benzene ring with only 3 hydrogens means 3 other things are attached to it. One of these other peaks has an integration of 3, right? So that could be a methyl group. It's probably a CH3. If it's a CH3, it's got to be the end of a carbon chain, right? That's a primary carbon at the end of a carbon chain. And then integration of 2 and 2 and 1, that starts giving us a lot of information here, right? We could start trying to put together something that might work here. And I believe in this region, 5.5, that's an OH. So that's why the others don't add up. I believe we're going to have an OH attached. And that's CH2. I would want to know the formula before I speculated too much more. But you can see how it's very, as opposed to IR, which leaves you lots of options, NMR is a lot more restrictive because of all the information it has, which means if you have an IR and an NMR, use the IR to get a couple of options, or even 10 options, based on your formula in the IR. And then you basically can go through your NMR and start knocking stuff off the list. It can't be this because my integration says I have 3 things attached to the benzene ring. And this isomer I drew only has 1 thing attached to the benzene ring. It can't be this because I only have 1 CH3 and not 2, so it can't be a methyl. Right, so it starts getting very limiting, and so you kind of usually bounce them off of each other. All right, so with 4 minutes left, talk about the trickiest part, which is peak shielding, or sorry, peak splitting. Peak splitting is based on the number of possible ways that you can get the signals to line up. And so if you have 2 H plus or 2 protons, they can either be both facing the same direction down, or they could be both facing up. Or the left one could be down and the right one up, or the right one down and the left one up. And so the number of different possibilities show up in our spectrum as basically a signal turns into a series of peaks that are attached to each other, basically, that are roughly bell curve shaped, because this is going to be the number of hydrogens nearby, and the number of arrangements that you can have follows a normal distribution. So they're going to tend to be bell curve shaped roughly. So for instance, if you look at the top right there, you can see the bell curve more obviously the more splitting you get. And what this actually tells us though is how many hydrogens are on the adjacent carbons. So for this molecule, these purple hydrogens, we know how many of the purple hydrogens we have based on the integration. We know how many hydrogens are next door by looking at the peak splitting. It's always going to show up as what's called the N+1 rule. You're going to have one more peak than the number of hydrogens next door. So for these purple hydrogens, there's only one hydrogen next door. So we would expect to see a doublet, basically two peaks really close together about the same height. This one, and oxygens basically throw all this off. They mess with the coupling because the energies are too far apart for this hydrogen versus this hydrogen. And so you can't count on peak splitting to take into account this. Peak splitting is really, it's the, like I said, it's the trickiest to wrap your head around. It's also the least reliable because things like oxygen, hydrogen's not showing up, not being counted. So for this hydrogen, we would expect to see it's either got 6 nearest neighbors, or if it couples with that one, it'd be 7 nearest neighbors. So we would expect to see either a heptet or a septet, 7 peaks, or an octet, where you have 8 peaks. And sometimes they get really close together, really hard to see. You kind of have to zoom in to see the peak splitting. But at the very least, we would know that this proton that has an integration of 1 has a whole bunch of carbons right next door to it. And then we would have a signal that was a much larger integral that only showed up as a doublet. So that really makes it really easy when you have the spectrum in front of you to say, okay, well, this peak goes with that carbon because big integral, few near neighbors, not very many neighbors nearby. This peak has a small integral with lots of neighbors nearby. Therefore, it goes to this one. All right, so we could, and so that the number of peaks in the signal is what's called the multiplicity. The multiplicity of each peak. So we've got its chemical shift, which is where it is, left to right, shielded, de-shielded. You've got the integral, and then you've got the multiplicity, are the most important things here. And I know I'm out of time, but I want to look at one of these real quick and walk through it with you very quickly. So if we have 2-chlorobutane, every single one of these hydrogens that's unique should show up as its own peak. So the hydrogen that's attached to the carbon is different than this methyl. And this CH2 is different than the methyl and this carbon, right? Because it's one carbon away from the chlorine. And this CH3 is different than that CH3 because it's 2 carbons away versus 1 carbon away. So because all of these carbons are unique, the protons attached to them will be unique. So we should expect 4 signals. 1, 2, 3, 4. The integral of them should be we find the smallest one. That's our CH1. And because it's closest to the chlorine, and chlorine's electronegative, it's the most downfield. So it's the most de-shielded, also the smallest integral, and it's got a whole bunch of peaks in there. It's got a lot of neighbors nearby. We would expect it to be 6 if we zoomed in on it. I'm not sure how high resolution this scan is. Hey, that's pretty good. We count these. 1, 2, 3, 4, 5, 6. So that means there are 5 nearby neighbors, which is what we see, right? This one's also a bunch of nearby neighbors. It's fairly de-shielded. And if we looked at the integration, it's right about double this. So this carbon, the hydrogens attached to that carbon go here. And out of these 2 methyls, we have 2 that are CH3, and we integrate them, we get 3 and 3. When we want to decide which is which, out of those, there are 2 ways to do it, and they should agree with each other usually. This CH3 is closer to the chlorine, so we would expect it to be more de-shielded. And it only has 1 next door neighbor. So we should see a doublet that is more de-shielded, which is what we see right here, right? And this one has 2 next door neighbors, nearby neighbors. So we should expect to see a triplet. And it should be more shielded because it's further from the chlorine, which is what we see. So if you don't know the structure ahead of time, it can be tricky to make sure all of the pieces fit together just right, but they should all be in agreement with each other. So again, just like with IR, get a couple of options on paper based on a formula, and then start knocking things off. It can't be this because of the splitting. That's a bad example because the splitting is the least reliable, like I said. Integration always works though. And the shielding can get a little bit hazy because sometimes things can switch from where you thought they were based on things like resonance or concentration, but you can usually go all the way down to NMR is a lot better at figuring out the total structure. It can't do R versus S, but everything else you can usually figure out from an NMR, especially if you have an IR to go along with it. So we'll end there. And I don't remember exactly what's on this quiz this weekend, but I think I probably will have you try to work through an NMR just like we did there. I'll give you a structure and the NMR, and you go through it and assign which peak goes with which hydrogens. And then maybe a little bit of pick the most likely mechanism.